Hey guys, welcome back. This is going to be AP Circuit Notes Part 4. And the next slide shows a picture of a meter, which we're going to use in here to measure voltage and resistance, but you also have to know how to measure current. So a digital multimeter is going to measure all of those things based on where you put the probe's ports and where you turn the dial. If we want to measure the voltage, we're going to put it to the volt with the line. The line across tells us that it's DC. This is what we get from a battery. And what we're doing is it is a voltage drop. So there's a difference in what it's measuring there to there. And whatever that difference is how much pressure is used up by that component. So we're going to get a value. Current has to be measured through. So the meter itself has to be part of the circuit, which we're not going to do because it's too easy to blow the fuses in them. But you'll have to be able to show it in a diagram. And you can see it goes to a different port. And now we're also going to the A with the straight lines, which tells us that it's direct current, as opposed to the sine curve for alternating current for these two. So current's going to be measured through the device. All right, so we have some resistor practice. These should add up to 110. So I'm going to have 10 plus 50 plus 20 plus 30 gives me 110. These are 4 that are the same in parallel, so that should be 10, but I'll do the math to show you. Now I have 3 that look like they're parallel. They're not. Only these 2 are parallel. This one's actually in series with the battery. So these are the same. I could replace it with a 5 ohm, and then that new 5 ohm would be in series with the 10 ohm, which would give me 15 ohms. These 2 are in parallel, very much like I put in the notes. They don't look geometrically parallel, but they are because the current splits. Some goes this way, some goes that way. They are the same value, so they're going to be 1/2. These 2 are in series, so they could be replaced by a 50, and then I have a 50 in parallel with a 50, which would be a 25. These 2 are in series, and these 2 are in series. These 2 would combine to be an 8 ohm resistor. These 2 would combine to be a 13 ohm resistor. And now my 8 ohm resistor and my 13 ohm resistor would be in parallel, and their equivalent would be in series with the 4 and the battery. So if I did 1 over 8 plus 1 over 13, I would get 4.95. And then I would have 4 plus 4.95. It's going to be 8.95. I'm back. I just want to check my email because I told some of the students I could unlock some tests for them. We're all good. It'd be helpful if I unfroze the screen, though. Okay. All right, so I have 4 12 ohm resistors, and I want to make them be 3 ohms. How would I do this? So I could put them all in parallel. I want them to be 18, I would do 1 in series and 2 in parallel. So 12 and 12 in parallel would be 6. 6 plus 12 would be 18. If I want to do 30, I would have 2 in series, which would be 24, and then 2 in parallel, which would be 6. And 48, I would just have them all in series. All right, so our series connection is going to have a single path from the battery through each circuit and element and then back to the battery. The current through each resistor is going to be the same. The voltage depends on the resistance. The sum of the voltage drops across the resistors equals the battery voltage. So all the way around, the voltage has to use up all of the voltage. The resistor that's going to get the most voltage is going to be the biggest resistor in series. Doesn't matter what order it is. The battery does not feel one and then the other. That's not how it works. As soon as that battery is connected, it feels all of them at once because it's pushing electrons that are already there. So batteries don't supply electrons. They supply the pressure. They supply the difference that makes them move. So in our picture here, our V total is going to be equal to the voltage drops across all of them. And because they're in series, the I total is going to be the same for all of them. In parallel, the current split, but the voltage is the same. So I have a picture here of 3 light bulbs. Each one of them has an independent path to this battery. So they're all getting all of that potential. But the current that's coming out, some's going this way, some's going that way, some's going that way. So in parallel, the voltages are the same, and the current is going to be the sum of the individuals. And current, because it is charged, has to be conserved. So we're not getting charge from nowhere. We're not getting current from nowhere. Current is not used up. Why does a battery stop working? Because the metals inside of it deteriorate from the chemical reaction that's happening. So in series, our current's the same, and in parallel, our current is equal to the partial currents. In series, our voltage will be the sum of the individual voltages. In parallel, the voltage is the same. So what I tell students to remember is ISVIP. This does not stand for I suck at Verley's physics. It stands for current, right? That's the symbol for current. Is the same in S series. V, voltage or potential, or Faraday called it EMF, right? So he called it the electromotive force, which is one of those things that we still do because historically that's what it was called. We don't like this because it doesn't have the right units of force. Is the same in parallel. So ISVIP. So we're going to add resistors together. We're going to apply ISVIP to our problems, and we're going to be able to solve complicated circuits. So first thing is you're going to make a V equals IR chart. Then you're going to try to find your totals, and then you're going to fill in everything based on ISVIP. Current's the same in series. Voltage is the same in parallel. ISVIP. Here's our chart. We put V equals IR across the top, and then we'll have our voltage for each one of our resistors going down. and then a total 1. All right, a 3 ohm, 8 ohm, and 5 ohm resistor are attached in parallel across a 24 volt power supply. Calculate the current through each resistor. What is the total resistance? So I'm going to say I have 3 ohm. I'm going to say I have 8 ohm. And I'm going to say I have 5 ohm. And I know that my voltage is 24 volts. All right, so these are all in parallel. So to add them together, I would do 1 over 3 plus 1 over 8 plus 1 over 5. And I got 1.52, so I'm just going to put 1.5 down. All right, now I know that V equals IR because I'm dealing with ideal conductors. So I'm going to get the total current. And my total current is going to be equal to our total voltage divided by our total resistance. And so this is going to be 24 divided by 1.5 or 16 amperes. All right, now I'm going to apply ISVIP. So ISVIP tells us that current's the same in series, voltage is the same in parallel. These are all parallel. They each have an individual path to the battery of 24 volts. They're each going to get 24 volts. And now I can solve for each one of their currents. So if I look at the first one, I can say that I1 is equal to V1 over R1. This is going to be 24 over 3 or 8 amperes. I can say that I2 is going to be V2 over R2. This is going to be 24 volts over 8 ohms or 3 amperes. Now, when I get to this point, there's 2 ways for us to solve the last one. One, I could just say I3 is V3 over R3, which is 24 volts over 5 ohms or 4.8 amperes. Or I can say, I know I have 16 amperes leaving my battery and going into my battery. And I know that of that 16 amperes, 8 amperes is going this way. And I know of that 16 amperes, 3 amperes is going that way. And I know that this has to be equal to the sum of all of those. I know that current has to be conserved. And so 8 plus 3 plus I3 is going to be equal to 16. So that tells me that I is going to be equal to 5. Now, why aren't they exactly the same? Well, I rounded here. This was like 1.52, so it made it a little bit off. All right, so series is going to be sharing a path and current being equal. Parallel is going to be multiple paths and voltage is going to be equal. So we didn't talk about that the last time we defined this. The equations for these, our equation sheet would say that RS is the summation of RI and RP would be 1 over R1 plus 1 over R2 plus ... The equation for Ohm's law is going to be V equals IR I'm going to make a chart to start with. I'm going to find my totals, and I'm going to use ISBIP, which doesn't stand for I suck at Berley's physics, but stands for current. Same in series, and voltage same in parallel. All right, now I have one that the same type thing, but now they're in series. I have my battery, then I have 1, I have 2, and I have 3. So again, I'm going to put in what I know. I'm going to put in my 3 ohm, my 8 ohm, my 5 ohm, and my 24 volts. I'm going to fill in my total to start with. So I can add these resistors. They share a path. I just got to add 3 plus 8 plus 5. That's going to give me 16. Now I can get my total current, because this is going to be my total voltage divided by my resistance. So that's going to be 24 over 16 is 1.5 amperes. Now I'm going to remember ISBIP, and ISBIP tells us that current's the same in series, and so all of these are getting 1.5. And to get the voltage, V1 is just going to be the current times the resistance. So I have 1.5 amperes times 3 ohms, which is 4.5 volts. For the second one, I have V2 equals I2 R2, so it's still getting 1.5 amperes times 8 ohms. And then again, our last one, we could do 2 ways. One, we could say I have 24 volts and I need to use this up. So what happens when I go across my first resistor, I lose 4.5 volts. So now I have 19.5 volts. The purpose of a resistor is to drop voltage. It dissipates it. That's a fancy physics word for losing energy. All right, so now I have 19.5. I'm going to go over the next resistor. This one tells me I have to lose 12 volts. So that means I have 7.5 volts. And I need to get to 0 before I get back to the battery. So this means this one has to make us drop 7.5 volts. Or I could say V3 equals I3 R3, which is going to be 1.5 amperes times 5 ohms, or 7.5 volts. So in this time, we had no rounding. We're in perfect agreement. All right, now I'm going to have a battery that's in series with one resistor and in parallel. So I'm going to have one resistor here that's in series, and I'm going to have 2 resistors that are in parallel. So the 2 resistors are in parallel, and the battery and the first resistor are in series. So I'm going to plug in what I know. This is still 24 volts. This is going to be 10 ohms. This is going to be 8 ohms. And this is going to be 5 ohms. All right, so to get my total resistance, I need to combine these 2 into 1. And so I would say that R23 is going to be 1 over 1 over R2 plus 1 over R3. And this is going to be 1 over 8 ohms plus 1 over 10 ohms. Which I think is 4.5, but I should do the math, right? Texas Instruments was 4.4. Rounding, huh? Where does this go in our chart? Nowhere, because it's not real, right? These are all real resistors and real values. This R23 is not real. We're using it as a tool. Why are we using it as a tool? Because now that I know which one could replace those two, this replacement one is in series with R1. And so if R1 is 5 and R23 is 4.4, then our total is 9.4. And now I can get I total. So I have 24 divided by 9.4. I got 2.55. That's going to make a rounding problem in this thing. This was 9.44. Why don't I try 24 divided by 9.44? 2.54. It's still going to be a rounding problem. So I'm going to round it up to 2. It's right in the middle. I'll do 2.6, knowing that I'm going to have some rounding differences in what my values are. All right, now I know ISVIP. ISVIP tells me that current is the same in series, voltage is the same in parallel. Are any of these resistors in series of each other? No. But they are in series with the battery. So coming out of the battery is this 2.6 amperes. Going into this battery is 2.6 amperes, and it has to go through that first resistor. There's nowhere else for it to go. So now I can get V1 is I1 R1. This is going to be 2.6 times 5 is going to be 13. All right, so what does this tell me? This tells me that my battery starts with 24, and I need to use up all 24 over the loop. When I go across R1, I'm losing 13. So that means I have 11. These are in parallel. They need to get the same potential. Are they going to share 11? Are they each going to get 5.5? No. Because I need to use it up over a loop. So some charge is going to go this path. So this one needs to get 11. And some of the charge is going to go in the other path when they split. Now, how much is going to go each way depends on what the resistor is. In our example here, more is going to go the 8 ohm way than the 10 ohm way. Why? It's a little bit easier. But the numbers are going to be close. All right, then I can get what the current is there. I really didn't pick easy numbers for myself, did I? The world's messy, right? So now I have 11 divided by 8. I have 1.4, and then I can do this 2 different ways again. So I know coming out of here is 2.6. And now I'm saying going down this way is 1.4. Is that right? 0.14. So what does that mean? The rest of it has to go this way. So that means that going this way has to be 1.2 amperes. Because these two have to add up to that, and these two have to add up to that. But I could also say, I know that I3 is going to be V3 over R3. And so that's going to be 11 divided by 10, which is 1.1. These are not exactly the same. We had to do some rounding.